Okay. Hello, everyone. This is the new session of the GLOSOLAN Spec webinar, and the webinar will be start very soon. And I see many colleagues is getting in the room, so we can wait 1 or 2 more minutes. And thank you very much for your participation. Just 1 minute more. Good morning, good afternoon, good evening, depending on where are you logging from. You're very welcome to join the new session of the GLOSOLAN Spec webinar. My name is Yi Pen from FAO's Global Partnership. I'm coordinating activities related to soil spectroscopy. I believe many of you have already joined our previous webinars. And this webinar will be the last session of this year. So I'm really pleased to have all of you join this webinar and to hear our scientists, our colleagues' knowledge and their research. And today's webinar, we have invited a very well-known scientist, soil scientist in our community, Professor Alex McBratney from University of Sydney, and also his PhD student, Sandra Evangelista. I hope I pronounced it correctly. And both of them will give us a talk, soil security via spectroscopy. On the panel list, we also have the colleagues from University of Sydney, Nicola Francos and Amin Shari Fifa. So they will be helping responding your questions. So before we start, I will just spend 1 or 2 minutes to briefly introduce how we proceed this webinar. The webinar will we will only enable the speakers and the panelists to turn on their camera and a microphone. So the participants won't be able to speak through the microphone, also won't be able to turn on your camera. But please feel free to write your message in the chat to communicate with other colleagues. And please also feel free to tell us where are you coming from. We will be very happy to know where you're coming from, and we really appreciate you spend the time, especially some colleagues from Latin America, which is midnight, to join us. We really appreciate that. In the meantime, if you have any questions during the webinar or after the presentation, and please feel free to write your question in the QA session. And my colleague will try to answer your question by typing the message, or we will select some questions, leave it after the presentation to have a live discussion. So as many of you probably know, the Professor Alex McBratney from University of Sydney is very well-known scientist in our community. He, in 2021, he already contributed one webinar to us and was very successful. That's also why we invited him again. He's very nice to decide, very willing to contribute to our webinar. And the subject of the webinar today is about the soil security via spectroscopy. It's because Professor McBratney proposed the soil security concept some years ago, and it's getting more and more interesting and popular. And so we would like to use this opportunity to hear more details and more instruction, more explanation about this concept. And also, we also would like to have some instruction from Professor McBratney to guide us how spectroscopy, this technology, how soil sensing can serve the soil security assessment related issues. So without further ado, I would like to give the floor to today's speaker. So Alex, please, floor is yours.
Okay, can you see me, hear me?
Yes.
Okay, good. Good. As Yi said, good morning, good afternoon, good evening, good night, depending on where you are in the world. I'm speaking to you from Sydney in Australia, where it's 5 minutes past 4 in the afternoon, something like that. And this talk is being given by myself and Sandra Evangelista, but it's also being helped facilitated by Nicholas Francos and Amin Sharififa, they are the two who are going to answer the questions. I don't know the answers to any of the questions, but they do, so they're going to answer the questions, which is wonderful. I'm going to share my screen and then we can get going. Let me just figure out how to do it. Let's see. Can you see my screen now? All good?
Yes.
Okay.
Yes. All good.
So today I'm going to talk a little bit about soil security as a concept. Not very much detail, just a very brief description of what we're doing with soil security. But during the talk, there are some references which you can read more deeply and learn much more about it. This whole talk and Sandra's talk will be available to you either as a PDF or the whole webinar will be recorded. So you can come back and find the references. You don't have to race to write them down. So let me just figure out how to change slides. Yes. Okay, so the way it works, I'm going to talk about very quickly about an introduction to soil security, and then Sandra is going to do the real part of the talk or the webinar, explain the relationship between indicators that you might wish to use in assessing soil security, how we can estimate those using spectroscopy. And we are going to talk about a slightly wider range of spectroscopies than we normally talk about in these webinars. It's not just about NIR today. So start off with the biggest of the big picture. There are 8 global existential challenges that we consider. We all know about them. Things like climate change and food security. Obviously, FAO works a lot on food security and nutrition security, but there's also energy security, human health, the ecosystem and environment, biodiversity protection, water security. But there is the 8th challenge is soil security itself. So when I use the term security, I'm using it very much in the same way as we use the term security when we talk about food security or water security. It's the same idea. And so if you read the paper listed there in Advances in Agronomy, you will get a whole list, a whole explanation of this concept. But what I'm saying here is that soil security itself is a global existential challenge, and securing soil will help to solve some of the other challenges which are listed there. And when we study soil security, we've decided that we need to study 5 different aspects, 5 different dimensions, which we call capacity and condition, which are biophysical dimensions, capital, which is an economic dimension, connectivity, which is a social dimension, and codification, which is a legalistic policy dimension. And if we're going to make soil secure, we need to look at all those dimensions. And we describe a way of assessing soil security in the paper listed there, which you can look at later. I think the important thing to remember, to realize, when we assess soil security, we assess it by a number of roles, a number of things that soil does. And we look at soil functions. So soil functions will be well known to people from the European Union area. And we list a whole row of functions there, including biomass production, carbon storage, biodiversity, habitat, and so on. And we also consider a range of threats. These are basically soil degradation processes, things like acidification or contamination, decarbonization, erosion, etc. In addition to those, we also consider some soil services. Now, the services we consider are not simply ecosystem services. They're listed there, ecosystem maintenance services, but these are also services which enhance the global existential challenges. So things like climate change mitigation, protection of biodiversity, food securing services, human health services, these are all supplied by soil as well. So it's a wider range of services. Once again, these are all described in the paper listed below, which you can find and read. These are published in Soil Security, so it's a free online journal. The other point that we make when we study soil security, unlike some other things like soil health, we say that one size does not fit all. In other words, if we were assessing a vertisol or a cambisol or a arena soil, then the target value for any particular soil indicator or property is likely to be different. We don't expect an arena soil to have the same clay content or, say, carbon content as a vertisol or a cambisol. So if we're looking for target values, it depends very much on the kind of soil. So we have a concept of a reference state or a reference soil for every soil in the world, and it's not the same for all soils. The next thing I want to explain is that when we compare the soil security concept with other concepts such as soil quality or protection or soil health, we try to cover more aspects of the roles and dimensions than the other concepts. And the one at the moment where everybody talks about, which is soil health covers a few of these dimensions and roles, but certainly is not comprehensive. So we are working on this soil security concept because it's much more comprehensive in dealing with all the aspects of soil and what soil can do for humanity and the planet. It's not a new concept. We found this book from the Soil Conservation Service of the US from 1941 called Towards Soil Security. So it's a concept that people realized back in the 1940s and the 1930s, but it's a concept that kind of got lost in the mists of time. And we are reinventing the concept and bringing it up to date and developing the whole framework for soil security, and which are described in those papers which I've talked about already. We have a workflow for assessing soil security, which you'll find in the Advances in Agronomy paper. We have a target area or a target point. For any assessment, we will need to assess some indicators. We'll need to find out where is the reference soil for the area that we're interested in for the soil. We'll need to estimate the utility of those indicators for the role, whether it be a service or a threat or a function. And then we'll need to aggregate our assessments to come up with an overall assessment. And if we look at roles and dimensions, And in this example, I'm going to very briefly give you, we're looking at the 2 dimensions of capacity and condition, which are the ones which are biophysical, and these ones most relate to what you can estimate using soil spectroscopy. And we're going to quickly look at the soil function called carbon storage, which is one that everybody's interested in at the moment. So let's look at that very quickly and very briefly. And once again, there is a paper which you can read at your leisure, which I will refer to later. So what's capacity? Capacity is the long-term functionality. It's difficult to change by human forcing. So the clay content of a soil, for example, would be an indicator of capacity. Hard to change by under human conditions. Or it may be that a property or an indicator that's easier to change, but we're looking at it under its natural condition. So capacity is more about long-term properties, natural condition. Condition is the short-term functionality, so generally measured by properties or indicators that are easy to change by human forcing. And you can evaluate that by comparing it with the reference state or the reference soil, which is often the soil under natural vegetation or under natural conditions. Just to remind us, we're looking at we're looking at soil function called carbon storage, but carbon storage is also related to the threat called decarbonization and the service of climate change mitigation. So the function, services and threats are not independent of each other. So evaluating one of the roles, whether it be a function or a threat, might also tell you about the service. In this case, we consider the indicators for carbon storage to be the total organic carbon, the inorganic carbon, which is often forgotten in all of these studies, and the mineral associated organic carbon. So we're going to look at these 3 together to give us an overall estimation. So in this case, all indicators, so I'm going to give you an example for Australia. All indicators are produced by digital soil mapping from sample data and available nationally at 90-meter resolution over 6 depth layers down to 2 meters. So that's the global soil map specifications. Remember, global soil map was invented for digital soil mapping before we had the global soil partnership. And that's also in Australia called the Soil and Landscape Grid of Australia, and was largely produced by the University of Sydney and CSIRO. So here's data for the mineral associated organic carbon and the values we have and the sampling we have, and that will give us an estimate of the mineral associated organic carbon for the whole country. And this tells you the upper limit of the mineral associated organic carbon, which we used using a quantile random forest kind of approach. Now, for every point where we want to estimate, we need a reference soil and a reference value. So to do that, we have a concept called pedogenomes, which we create soils with areas with similar soil forming factors. So in Australia, we have about 1,350 pedogenomes. And I'd like to tell you today that we're currently working on a global pedogenome map at this very moment. So in a few months, we'll be able to show you what it looks like for the whole world. But here we have the map for Australia. So each one of those slightly different colored areas is one area where we have the same soil forming factors, but within that area we have what we call genosoils and phenosoils. So the genosoils are the reference soils. So they're the ones that have been relatively unaltered, maybe under natural vegetation, and the phenosoils are the areas which have been altered by human intervention or human forcing. So in our way of doing this estimation, when we estimate capacity, we look at the genosoil organic carbon content, inorganic carbon content, and the upper limit of the mineral associated carbon. That's the soil that's less disturbed. So for any particular area in Australia, we look at its genosoil to see what the target value should be if we're, say, when we do the estimation of condition. And then to estimate the condition, we look at the difference between the current value in the phenosoil from the genosoil, or the current value of the total organic carbon, the inorganic carbon, and the ratio of the current mineral associated carbon with the upper value of the mineral associated carbon. So this is the genosoil total organic carbon, and this shows you the capacity for storing carbon. And for most of Australia, it's not very high because most of Australia is quite arid, so the total organic carbon storage is not very high. But this is the important part, and I've missed a lot of steps here, so we can be quick. The condition of the total, where the condition of the total organic carbon is more than 0.9. Sorry, it's less than 0.9. So that's the area where we've lost carbon. That's by comparing the phenosoil and the genosoil. So the red areas, we have lost carbon. So we can highlight those areas, and these are the soil condition, or if you want to use the term soil health hotspots, these are the areas where we have to look and try and improve the carbon content of these soils. We know they're capable of higher carbon contents because we know from the genosoil they have higher carbon contents. So we need to figure out how to put the carbon back in those areas. And remember, the reference soils are different in different places, so the target values are different in different places. All of that is described in a paper. It's in Geoderma, which you can look up afterwards. As I said, you have access to all these slides. So the main findings up here are we can't do continental or country extent soil capacity and condition or health assessment. We can assess for this function, in this case, carbon storage. Obviously, when we do these national type things, we need localized testing and updating. We do need more sampling of our genosoils, because what tends to happen in national and even regional sampling is we tend to focus in on the agricultural soils, and we don't tend to focus in on the more natural soils. The ones the ecologists would look at are not the ones the agriculturalists look at. So we need to do more sampling of our genosoils and soils in natural condition. So the assessment and mapping can drive localized monitoring and management decisions, and can contribute simultaneously to sustainable food production and climate change mitigation. And I think that's the most important point. Why are we doing this soil security assessment? For that purpose. So where are we heading to next? So I've only talked about what, I'll give you one example for one soil function, where there are many more soil functions, services and threats that need to be evaluated to get an overall picture of soil security. So we here in Sydney are working our way through all of these kind of evaluations at the moment. But which leads me to the main point of this whole webinar: how useful is soil spectroscopy for evaluating soil functions, services and threats? I'd like to acknowledge that this work is funded by the Australian Research Council on a laureate fellowship. So they're spending many millions of dollars in working on soil security. We have a conference coming up on global soil security in Winnipeg, Canada in July next year. More details will follow. It's part of a bigger conference with IUSS and the Canadian Society of Soil Science. More details there. I'd just like to thank you all for listening, because you're not going to hear from me again much today. And at this point, I'm going to hand over to my colleague, Sandra Evangelista. So I'm going to stop sharing, and thanks very much.
Thank you, Alex, for that nice introduction into soil security and for that example. I will share my screen. Is that visible for everyone? So I'll be answering this question. And hi, everyone, I am Sandra. So how can we use soil spectroscopy for soil security? Looking at 4 spectral instruments that are widely used or emerging, here they are in the order of most commonly used to least used. Vis-NIR has been around or used in the last 20 to 30 years, whereas mid-infrared it's been used in the last 10 to 20 years, XRF in the last 10 years, and LIBS really only in the last 5 years. There are also handheld models of each, which makes it possible for in-field assessments, for in situ measurements and immediate results. And these instruments sit between the X-rays and mid-infrared range, and some of these are overlapping. So very briefly, how we generally use these instruments is we take the soil sample, we collect the spectra in the field or in the lab, and together with the lab analysis and the spectra using models, we can predict several soil properties. For example, organic carbon, sand, silt, clay, and all these predicted properties have different performance accuracies. There are, of course, many advantages to soil spectroscopy, which we all know, and it makes it very attractive in soil science. We all know how expensive and time-consuming it can be when you have to send your samples off to the lab. So earlier, Alex mentioned the 5 dimensions of soil security and the 3 roles of soil, and these are key in assessing soil security. So the soil security assessment framework is a systematic evaluation of soils that aims to evaluate the full suite of soil roles across each of the dimensions. Of these dimensions, capacity and condition are the most straightforward in terms of assessing using spectroscopy, because you can measure it using soil properties, so spectroscopy can be applied. With there being 8 soil functions, 7 services, and 8 threats to soil for each biophysical dimension, there are about 46 potential evaluations that we can do using spectroscopy. In our paper where we propose this framework, there are about 43 potential soil indicators that are listed so far to evaluate the roles under capacity and condition. And you can find these in the paper there. So these indicators that were listed, they're a combination of expert opinion, pragmatic indicators, and surrogates. For surrogate indicators, we have put out another paper last year. Unfortunately, we don't have time to go to the detail today, but this may be of interest to you, and I've just kept it down here in the bottom. And it's important to note that these indicators are not exhaustive list, and it also depends on data availability. So here is an example for soil functions. On the left, we have the full list of functions. On the right side, we have indicators for capacity and condition. And as Alex mentioned earlier, for indicators under capacity, these are more inherent soil properties that are harder to modify. For example, clay, silt, and sand, mineral type, not easily changed in our time scale. Whereas condition, these are more dynamic soil properties that are easily influenced by how the soil is managed, like pH and bulk density. So we may notice that a certain indicator can be used to assess multiple functions. For example, CEC can be used for looking at biomass, nutrient cycle, remediating contaminants. So if we highlight cation exchange capacity, which is useful for all these roles, we want to know how well is it estimated. So we investigated this by looking at the literature, finding any evidence of performance accuracies, and these were mostly reported as R² and LCCC. And then we averaged these for each indicator. And then using a classification by Watini, Nung et al. In 2022, we classified the evidences as A, well estimated, B, fairly well estimated, C, reasonably, D, poorly, and unknown. Unknown, it was either that we couldn't find any evidence, but also some of them had estimated the property but did not report any performance accuracies. So back to CEC for our spectral instruments. Across the board, NIR, MIR, and LIBS could estimate the indicator fairly well. Only XRF produced a reasonable estimation. Looking at some more examples, we can see that total carbon content, organic carbon, and pH, they are useful for a range of many roles. So for total carbon content, it performed pretty well across the board of the 4 instruments. Organic carbon, only XRF had some trouble. pH was a bit inconsistent across the instruments. Some were performed better than others. Again, some more examples, but perhaps for some that were not very well estimated. EC was poorly estimated by NIR and MIR, but was a bit better in XRF and LIBS. Bulk density was reasonable for NIR and MIR, poorly estimated by XRF, but LIBS was unknown. Microbial biomass was inconsistent across the 4 instruments. Was a bit of a divide here. NIR and MIR were much better than XRF and LIBS. And for PLFA, evidence was found, or no evidence was found for XRF and LIBS. And there's a bunch more indicators, and the full list of these are to be published in the future. To summarize, the indicators that were well estimated or classified as A for these instruments, this NIR, it looks like it was well estimated carbon-related indicators much better. MIR, there was quite outstanding with a long list of indicators that it could estimate very well. XRF was able to estimate elemental composition quite well, and LIBS, similar with LIBS. On the other hand, indicators that were poorly estimated or classified as D, VISNIA had, we see that VISNIA had micronutrients, a longer list of indicators that weren't well estimated. MIR, mostly to do with elemental composition, but this could be because these 2 were not designed to estimate micronutrients or elemental composition, as well as XRF and LIBS, which were designed to estimate or measure elements. And although we saw XRF and LIBS estimate elements quite well, there's a long list of them. So some of them were better predicted than others. So for the unknowns across all the instruments, these were redox potential, redox buffering capacity, denitrification, and tensile strength, which which are really dependent on in situ conditions. For tensile strength, we can estimate it using clay content and clay mineral, but we couldn't find as much evidence on this. For rootable soil depth and deep drainage, these indicators are more soil profile characteristics. So these would be more difficult for spectroscopy to pick up. Looking at these indicators again, these are quite useful we can still see that these are quite useful for a range of roles. So what other ways can we estimate them? So we can use pedotransfer functions, which uses equations to predict a property from other soil properties known and that are easier to measure. And where we apply spectroscopy is called soil spectral inference. And this predicts soil properties from a spectrum directly or indirectly predicts using predicted properties from the spectra. And from this, there is a spectral inference system that was developed at the University of Sydney to systematically predict soil properties using a collection of pedotransfer functions using lab and spectral data. More information on SynFIRS with a given live demo was actually given in a previous workshop, and you can find it in the QR code here if you are interested. So with soil security, there is the reference soil selection, which Alex mentioned earlier. We commonly use the concept of pedogenons, which are, again, soils formed or developed under similar forming factors. And spectroscopy can be used to compare or assess the indicators for genus soils and phenus soils. And the idea of the reference soil, again, is important to observe how much the soil has been modified or by various factors, including human impact and management. And so spectroscopy can be a very important tool here to observe soil change. Considering the future of spectroscopy in soil security, we have seen it used effectively for capacity and condition, but can it also be used for other dimensions, perhaps indirectly? For example, maybe capital. Could we use spectroscopy for to measure carbon for carbon stocks? And more work on this is to be done. Secondly, there's been some work emerging combining spectral analyzers, which gets the complementary features of a range of analyzers to get the best features and improve assessments and get better accuracies. I think I also saw in the chat that Rusbe from Eccentric did a NIR and XRF multi-analyzer, which is awesome. Thank you for sharing that, Rusbe. Another example, which I have here, is by Harman, where they combine XRF, Raman spectroscopy, and LIBS to provide better performance for analysis than any individual analyzer. And to conclude, spectroscopy does prove to be an effective way to estimate these indicators for soil security assessments, and it is a step forward to providing an overall soil security assessment. But also, several indicators remain uninvestigated. Spectroscopy is important for monitoring soil capacity and condition, which is synonymous with soil health. And the information that we can derive from this analytical technique can contribute to policy development, which will lead us to more meaningful and lasting impact to secure soils into the future. And with that, I would like to acknowledge ARC as well and thank them for funding this project. Special thanks to Nicholas and Amin for being in the chat to help answer your questions during the presentation. Thank you very much. I would also like to thank Alex, Budiman, Amin, and Nicholas again, and also Watini Nang for helping me in completing the table of results. Thank you, everyone, and back to you, Yi.
Thank you very much, Sandra and Alex, both. I think it's a very, very interesting introduction and to briefly explain and also to introduce the concept of the soil security and how soil spectroscopy can serve this concept for the future assessment. I saw some the colleagues start to writing the questions, and we can give them a little bit time because I believe they're typing. So before we choose the questions to answer live, actually I have a question to Alex. The last time I take this advantage to first ask the question because it's very interesting talk and also, I have this question in my work as well because I need to answer the question to the colleagues in the community around the world. It's not a research question; it's actually a practical question, and I also know it's very hard to answer this question black or white. So I just would like to hear your opinion, your vision about this, and to share with us. As just now, Sandra showed some results. We have visible near-infrared spectroscopy, mid-infrared XRF, and LEAPS, and also different sensor provide a different result in terms of the accuracy. And we also can see MIR performs better than in general, perform better than other instruments. And then the question comes, of course, in the end, Sandra also concluded it's better to have a fusion of the data because a different sensor has a different advantages. The best is we can collect the data, different type of the data in the same time, because when the soil come to the lab, if the financially allowed, we can have all type of the instrument and collect the data in once, or we archive the sample. And when in the future we have funding to buy more instrument, and then we rescan the data. But the reality in a country, especially in most of the developing countries, the funding is a big issue, which doesn't allow labs to buy all the instruments in once. Then the decision needs to be made. What instrument should be bought the first? If we talk about the accuracy, of course, MIR is giving the better accuracy. So from that point of view, we highly recommend to do the MIR. And then if we come to from the time and the cost-effective point of view, and also if, as Alex said, at this stage, most of people very much interested about the carbon estimation. So, of course, from my knowledge, if we only talk about the carbon estimation using spectroscopy, visible near-infrared in terms of accuracy probably is more or less enough, and also requires less sample preparation compared to the MIR, the fine grinding. So in this sense, of course, if we look at the long-term planning, MIR is always better. But some reality in the developing countries, they cannot make a long-term plan. So in that sense, they always come to me, come to FAO to ask, what is your suggestion about in which range of spectrometer we need to buy? And I know it's a very hard question to answer. So if you can share some of your opinion or your perspective in this regard, I think it would be very helpful for the countries to start their spectroscopy lab and slowly develop. Thank you.
Can you hear me? Yes. Yeah. Well, thanks for that extraordinarily difficult question, Yi. I don't think there's any definitive answer about this, but I'll tell you my thoughts about it. And perhaps I don't look at it from exactly the same perspective as you. You are working for a global organization. You have countries coming to ask you what's the best thing to do. I think more from a scientific point of view, but I can understand what you're trying to achieve. two things though. First of all, I'd say two things about the future. In the future, we won't just be looking at carbon. That in this time at the moment, everybody's looking at carbon, but I think that that's just something for 5 or 10 years. In the future, we'll be looking at many other soil properties. So I think so if I'm planning a future for a country which is developing, I would say don't just think about carbon, although carbon might be one of the things that you want to look at. That's also why I say think about soil security. Don't think about soil health, because soil health is too narrow. It looks at too few things. It only looks at one function, which is biomass production. You need to think about in a wider sense. So if I'm thinking to the future, and this is the future of any country, whether it be a country like Australia or any country in the world, highly developed, developing, in the global west or the global north or whatever these words are. I know we talk about the global south, but Australia is actually in the south, but we're apparently not in the global south. Anyway, if we're in any of these parts of the world, I think we have the same future. We're looking at a wider range of things. If we're talking about agriculture, it will become net zero and it'll become nature positive. And we need to think of all the soil properties that will make it net zero and nature positive at the same time. We have to do both of those things together. So I think we'll be looking at a much wider range of properties. We'll be looking at a wider concept than soil health. That's why we bring you soil security, which is a wider range of properties. That being the case, then I think the long-term investment probably has to be MIR. It probably has to be something that will give you as many properties as possible with one spectrum. Remember, you do it with one spectrum. That's the great advantage. You know, the work that was, we can estimate 50 properties very well with MIR. So I would go for that. The work that has not been done is whether we can do field MIR, okay? And still we don't have many results, or we don't have good results for using it in the field. So that's research work that still needs to be done. If you're really interested in getting estimates of soil properties in the field, if you're doing agronomy, for example, and you want a decision in the field, then probably NIR or XRF are the methods to use, because both of those instruments work in the field. At this point, there is not enough research on LIBS to tell us whether it's going to be good in the lab or in the field. So, but we put it into this analysis because we see more papers being published in this area. But just to summarize, I think we have to look on a 5 or 10 year time frame. I think we're going to look at many soil properties to make our agriculture, as I said, net zero and nature positive. In other words, we're going to try and do a carbon balance or an energy balance on our farms, and we're also going to try to improve the ecosystem services and the biodiversity of our soil and our landscape. If we're going to do that together, we're going to look at many soil properties. So I think we're probably looking at MIR as an effective way of doing it. The cost differential is in the initial cost of the instrument, but once you have the instrument, it doesn't cost doesn't cost very much more to produce an MIR spectrum than it does to produce a NIR spectrum. And there's so much more information in the MIR spectrum. So I think you asked me a very good question, a very difficult question, and I hope my answer is not too biased. Thank you.
Thank you very much, Alex. I'm sorry I asked you. The first question is already very, very difficult. The reason it's difficult is because since I started this job, and constantly as a colleague around the world came to me with this question, and I also found it very difficult to answer.
But let me reiterate, it's a very good question. It is the most important question. There's no, in this soil spectroscopy exercise, it is the most important question, no doubt.
Thank you very much. So I just came up an idea because you explained in a really systematic way. Maybe we also can consider to write a small article or small guideline as a FAO guideline to give the colleagues. I mean, not a research article, but it's like a more guideline or introduction in this direction to be published as a FAO publication, so we can distribute to the countries. Then so they can have a better understanding to make their own decision.
Absolutely, and I think it's, as long as if we explain the positives and negatives of each, then it's a question of them making a decision and a balance. But the other thing I will say is that the cost of all this instrumentation is coming down for all of these spectroscopy. So as time passes, the cost becomes less. So that's a big advantage. So anyway, I shouldn't say any more. I said too much, but
no, I think it's good to hear about your opinion, and maybe later on I can get in contact with Sandra, and then we can see how to write this short kind of a guideline, just to provide some evidence and some recommendations. Yeah.
So like, the important point is this, and the reason why we're doing this webinar today is this. We feel that if we want to assess soil and its security into the future, whether we want to maintain our soil or improve it into the future, we're going to have to measure a lot of indicators, not just 3 or 4, but quite a lot, if we want to look at all the aspects of things that soil can do. And I believe the most efficient way to do that is using spectroscopy. I think spectroscopy is the key to doing that efficiently and cost effectively. And then it's just a question of which spectroscopy do we use. And that's why we did this analysis, because before we did this analysis, we didn't know the answer. Okay.
Yeah, I think I have to say this analysis is very useful. It's very useful. Yeah, I think it would be a good idea. I will follow it up. Thank you very much. And I saw the question. It's like a flooding coming up. I know if Asim and Nicholas, if you see any questions interested, can be discussed, answer alive. Sandra, because I have been discussing with Alex, I didn't really pay attention because in a very short period of time came a lot of questions. Nicola and Amin?
Yes, sorry, I was checking the questions because there are many, and it's a little difficult to decide which of the questions could be the most relevant here, because actually there are some that are very good. One of them, for example, is do you think that the laser-induced breakdown spectroscopy is a promising technique for soil fertility analysis? I think that this question was partially answered there. If we consider the cation capacity, carbon texture, and pH. Let me see. Which type of spectroscopy is better for soil salinity?
Yeah, maybe we can talk a little bit, Alex, if it's possible. We can talk a little bit about the salinity. Actually, yeah, there are some countries, especially from Middle East and North Africa. I guess you know in this region they have a big problem of the Near East, also big problem of the salinity. So they are also interested in how to use the spectroscopy, this technology, to assess the salinity as well.
I'm going to defer that question to Sandra. She did have some result on electrical conductivity.
Sorry, can you please repeat the question?
So the question is, you know, in a region of the Middle East, Near East, North Africa, even Central Asia, they have a big issue of the salinity. I would say that's the top priority for some of the countries even. So and also in this region, soil spectroscopy, this technology is not really developed. So for them, it's a new technology. But they would like to develop this technology within their country. But they would like to know how they can use this technology to help or to assess, to monitor the soil salinity issues in their country or related issues.
Right. Okay. So I do have some results for the for indicators for ESP, exchangeable sodium capacity, and exchangeable sodium percentage, which was found to be, just looking it up now, it was unknown for LIBS, but it was reasonably estimated using the other three. I think it seems to be yeah, or maybe some other indicators that might be useful to assess sodium percentage. For salinity.
You also gave some results on electrical conductivity, Sandra.
Yes. Yes, so I think assessing the indicators relating to salinity, which is listed in the results, using a range of different indicators like EC, ESP, and then for the instrument's performance, it's as you saw for EC, was not very well estimated. It was poorly estimated by NIR and MIR, and reasonably estimated by XRF and LIBS, but ESP as well is only reasonably estimated by the three except LIBS.
Yeah, so my intuition is that if we're worried about estimating salinity by electrical conductivity, I think XRF is good at elemental analysis. So we're looking for sodium or chlorine. So it just depends on what we're particularly looking for. NIR and MIR are not so good at estimating individual elements, generally speaking. That's why in our work here we routinely do MIR and XRF. We do both, and the advantage, of course, is that XRF is relatively easy to do. XRF works both well in the lab and in the field as well. So, but once again, XRF is really about elemental compositions. So anything that is impacted by elements, XRF's pretty good.
Yeah, I think the back to just now we discussed also, it's also important to let the country and the labs know which instrument is better for what property or element, because there is misconception is some of the colleagues or labs just simply believe one instrument can solve all can answer all the questions.
No.
And they need to, I think the world need to know no single instrument is able to does everything.
Yeah, no, that's absolutely correct. So going back to your question, I think MIR gives you the most indicators for the investment, but it doesn't give you everything. And then you need to decide which is the second best. If I had an MIR, then I would go to XRF, because MIR will tell you most things that NIR will tell you, but it'll tell you more things. But XRF will tell you different things from MIR. So if I have to put two together, it's MIR and XRF go together, because they're complementary. They give you slightly different information, but when you put them together, it gives you more information.
Okay, thank you. Note is taken. I think that this information also very helpful for my work.
Hopefully for everyone that's listening, I hope. Yeah.
Okay, thank you very much. And I saw there is still many questions, and certainly we won't be able to answer all of the questions on live. My suggestion is if Sandra, Nicola, and Amin, if you can write your email address in the chat to everyone, so the colleagues around the world will be able to send an email to you if they have any questions, or if they are looking for any collaborations, or if they're looking for some guidance or supervision. So that will be very helpful. So you can write to, I think you need to choose to everyone, because what you wrote was to host and a panelist. So you have to choose, write to everyone. So then everyone will be able to see. Yeah, everyone will be able to see your address. So, so colleagues, time goes fast. We passed 1 hour, and it was a very nice experience to hear your sharing, your knowledge. And I personally learned a lot. And I also found that what we can work together, we can write something together, and to facilitate the world, the community. I found it's going to be extremely useful, and so I will follow up with Sandra later on, and we see how we can develop a kind of a guideline or introduction in this regard. And we will, in a GLOSOLAN Spec, in FAO, we will continue organize such webinar and to share the scientists' knowledge to the world. And if you have any questions, please feel free to reach me out as well, because it's my full-time job to facilitate soil spectroscopy related activities. And I would like to thank to the Alex, Sandra, Nicola, and Amin again, also the team in the University of Sydney. And we have been collaborating really well since quite some years. And we also delivered quite some nice material, including video, written document, webinars, and I'm really happy and looking forward to have continue such collaboration. And so thank you very much, and I hope to see you, to have a next opportunity to work with you again.
I'd like to thank you, Yi, and I'd like to thank the audience. This has been an honor a privilege and a thrill to talk to you today, and we hope to continue the conversation.
So the last is just to because it's been always difficult for us to choose the time because it's a global thing. But just to let everyone know, we are going. We have recorded this webinar, and we will upload the recordings. We will upload the slides as open public resources. So please regularly check our website where you did the registration. So you will be able to watch recordings and download the slides. I think in short time, within 1 week, we will upload. So thank you very much. And I wish all of you have a nice evening in Australia. And we will start for the day in Europe. Okay. Thank you.
Thank
Bye.
you.